Though turbulence is not particularly easy to define, it's not hard to find examples. In these, we can find certain common characteristics. One of the most apparent is disorder, as can be seen in this channel flow. The disorder is of such a fundamental nature that the flow never is reproducible in detail, no matter how carefully one attempts to reproduce all the boundary conditions. Although the details are not reproducible, averages over suitably large intervals of space or time may be very well defined and stable. Disorder, then, is a necessary factor in any definition of turbulence. It is not, however, sufficient. Here is a pretty disordered fluid motion, but it would be unwise to include it in turbulence. A wave field like this does very little mixing, and mixing is an essential feature of turbulent motion. The mixing action of turbulence can lead to complete blending if the volume is confined, or to the dilution, which is the only thing that makes pollution like this or this barely tolerable. Another characteristic of turbulence is the presence of vorticity. In a turbulent field, the vorticity is distributed continuously but irregularly and in all three dimensions. So turbulent flow has more than one distinguishing characteristic or symptom. Perhaps we can borrow the word syndrome from pathology and say that we have a defining syndrome or set of symptoms for turbulence. These are disorder, irreproducible in detail, efficient mixing, and vorticity, irregularly distributed in three dimensions. This definition effectively isolates turbulence from various kinds of wave motion. It also eliminates all two-dimensional flows. Something roughly like turbulent motion can exist in two dimensions. Weather systems on a large scale represent nearly two-dimensional flows. However, the characteristics of such flows are in many ways so different that it is perhaps unwise to include them in turbulence. Some flows, like this jet, are clearly turbulent. Others are equally clearly not. What is it that determines whether or not a flow is turbulent? To help answer this question, we'll use this apparatus, which is a version of that used by Hagen over 125 years ago in a study of flow through pipes. In these two tanks, we have two different glycerin-water mixtures. One mixture has viscosity about 3 times that of the other. The valve permits us to obtain any combination of the two mixtures. The fluid is pumped by this constant displacement pump so that the flow rate remains the same no matter how the mixing valve is set. Our pipe begins here. Midway down the pipe, we start a manometer tube which we carry downstream so that we can see the upstream pressure simultaneously with the end of the tube, where the pressure is atmospheric. The manometer reading will give us a measure of the average pressure gradient along the tube. Now we start the pump. The manometer reads about 10 units. Now I change the valve setting to reduce the viscosity. As the low viscosity fluid flows into the pipe, the manometer reading decreases. Once more I change the valve setting to still lower viscosity. But look here. We have increased the pressure difference, which means that we have increased the drag. Let's look at it again. I increase the viscosity, and down goes the pressure difference. I decrease it again. Up it goes. Now, let us look at the fluid coming out of the end of this pipe. Notice that the fluid comes out in quite a smooth stream. We have the intermediate viscosity with its corresponding low pressure difference. Now let's go to the lower viscosity with the high pressure gradient. The edges of the stream coming out of the tube have become blurred. If we look at this stream in slow motion, we can see that the blurring is resolved into an irregular motion of the surface. The flow has become turbulent, and the onset of turbulence in the pipe has revealed itself both in the irregular motion of the fluid stream and in the greatly increased drag in the tube. In the early 1880s, Osborne Reynolds did a series of experiments on flow-through tubes and came to the conclusion that the criterion for the onset of turbulence was a dimensionless function of the flow parameters, which has since been called the Reynolds number. There is usually a certain amount of arbitrariness in the definition of a Reynolds number, but for pipe flow, let's take it as the diameter multiplied by the average speed divided by the kinematic viscosity. Although the question is still under investigation, it seems that if the Reynolds number, so defined, is appreciably less than 2,000, the fluid is not turbulent. In this experiment, we have deliberately made the input conditions somewhat abrupt. Turbulence occurs at a Reynolds number not much over 2,000. However, if we improve the entrance conditions by putting a nicely flared funnel at the upstream end, we can delay the transition to turbulence to a much higher Reynolds number. Now we have increased the flow rate and further decreased the viscosity. With very great care, it is possible to push the Reynolds number up as high as nearly 100,000 without turbulence. However, here we can reach only about 8,000. The onset of turbulence depends upon the growth of perturbations because of an instability. For example, at this Reynolds number, the flow alternates between laminar and turbulent modes, apparently randomly, depending, presumably, on some random variations of the perturbations. Prominent in our defining syndrome was the word mixing. What about mixing? Let's modify our experiment by introducing a thin streamer of dye into the flow. Notice that the dye forms a thin filament which maintains its identity with very little change right down the tube. The only mixing is molecular, and the concentration gradients are so small that this process is very slow. This is laminar flow. Now we increase the Reynolds number. At the onset of turbulence, our dye filament seems to explode, and the dye is rapidly mixed across the tube. If we want to, we can regard the increase in pressure difference as a manifestation of mixing too. Mixing of momentum. In laminar pipe flow, the velocity profile is parabolic. Near the walls, there is a considerable quantity of relatively slowly moving fluid. Dye, injected near the wall, marks some slowly moving fluid. When it leaves the pipe, it falls with a steep trajectory. Notice that the slowly moving fluid near the top of the pipe also falls steeply. The rapidly moving fluid from the middle of the tube falls with a flat trajectory. Compared with laminar flow, in turbulent flow, the mixing of momentum causes the velocity to be much more nearly uniform. The fastest fluid is not quite so fast, and there is very little slowly moving fluid. What little there is can be dragged along with the rest when it leaves the pipe. Nevertheless, the velocity must vanish at the wall, so we can regard the wall as a sink for momentum. Turbulence increases the rate at which momentum is transferred toward the wall. Thus, with turbulence, we need a larger pressure gradient to replace the momentum lost to the wall. Although the principal motion of these bubble patches is downstream, there is a very appreciable cross-stream component. Fluid moving across the stream in this way tends to carry its properties with it. It is these cross-stream velocities which do the mixing. For example, the momentum close to the wall is appreciably less than that in the center of the stream. The cross-stream motion carries low momentum fluid into the center of the stream and high momentum fluid toward the wall. Thus, the turbulence transports momentum. In this shot of the Fraser River at Hell's Gate, we can see great volumes of slow-moving fluid which come up from near the bottom and very much reduce the average speed of the surface flow. Turbulence can transport more than momentum. With scalars, such as dye and heat, mixing may be primarily a matter of stirring a fluid which is already grossly homogeneous. On the other hand, if we have a mean property gradient, the most important effect of the mixing may be a transport of some property, as dye is transported across this channel. The wall here has been deliberately roughened in order to increase the ratio of turbulent to mean flow speeds. The dye also helps us examine the velocity field. The blue dye is injected at the center of the channel where the flow is fastest. The red dye is injected near the wall into the slowly moving fluid. Notice how, even at the same distance from the wall, the filaments of blue dye move more rapidly than do the red dye filaments. The forward momentum of fluid moving towards the wall is on the average greater than that of fluid moving away from the wall. The region near the wall, then, continuously gains momentum at the expense of the region near the center of the flow. Since rate of change of momentum is force, and force per unit area is stress, we see that the presence of the turbulence produces a stress, the Reynolds stress, within the fluid. The Reynolds stress is additional to the ordinary viscous shearing stress and produces the increase in drag which we found in our pipe flow when it became turbulent. Now, let's have a closer look at the mixing of a scalar. In this vessel, we have two miscible liquids, one floating on top of the other. If we leave them for a week or so, molecular diffusion will do a fair job of mixing them. Much more thorough mixing can be accomplished in less than a minute if we make the fluid turbulent. In this case, too, the end result is intimate mingling on a molecular scale, although the turbulent motions themselves are not much smaller than about a millimeter. The role of the turbulence is to make the inhomogeneities more vulnerable to the effects of molecular diffusion. Perhaps this can be clarified by animation. Let us suppose we have a blob of something which we plan to mix into the surrounding fluid. If the fluid is turbulent, the irregular motion will result in a strain, which will pull out the blob into a greatly elongated form like this. In turbulence, there is a great range of different scales of motion. At the same time as the blob is being pulled out, smaller scales are distorting it. And smaller scales still produce an even finer grain structure. Eventually, the interfacial area becomes so large and the property gradient so steep that molecular diffusion is able to act quickly and produce efficient mixing. In reality, of course, All the events we saw sequentially occur simultaneously. One of the curious properties of turbulence is the fact that although the Reynolds number is very important in determining whether or not a particular flow will be turbulent, once it is turbulent, the value of the Reynolds number is of very little importance as far as the large-scale motion is concerned. These two jets look pretty much the same. On the large scale, a turbulent jet is a turbulent jet, period. However, if we turn our attention to the small-scale motions, as seen in these shadow graphs, the effect of the Reynolds number is pretty clear. Notice how much finer grained is the structure in the higher Reynolds number jet. The reason for this can be understood if we consider the energy dissipated. In these two jets, the Reynolds number difference is produced by having different viscosities. All other conditions are the same, including the energy input into the jet. Therefore, the two jets dissipate energy at the same rate. Now, energy dissipation in a Newtonian fluid is given by the viscosity multiplied by the mean square of the strain rate. Dimensionally, viscosity multiplied by the speed squared divided by some characteristic length squared. This can be written. In the two jets, we have the same energy dissipation and the same characteristic speed, but have different viscosities. Therefore, the length scales must also differ. The high Reynolds number jet with low viscosity must correspondingly have a smaller characteristic length scale. This leads us to one of the most important concepts in the study of turbulence, the idea of the energy cascade. As we have seen, under certain circumstances, a large-scale motion can become turbulent. Some of the energy in the large-scale motion is converted into turbulent energy. The largest scales of the turbulence are usually smaller than, although comparable with, the scale of the basic mean flow. However, usually these large-scale motions are themselves unstable and break into smaller scale motions which take energy from them. Finally, the energy passes down to scales, like those revealed by this shadow graph, which are so small that the Reynolds number is too low for instability. The energy is dissipated by the action of viscosity. The analogy with a cascade of water is a useful one. Here, the only property of the flow at the top, which matters at the bottom, is the rate at which water passes down the cascade. Similarly, in the turbulent energy cascade, at the smaller scales of motion, it is only the rate of energy dissipation which is of any consequence. This rate, together with the viscosity, determines the size of the smaller scales of motion. At high enough Reynolds number, the small-scale turbulence loses all directional orientation. It becomes isotropic. Figuratively, it doesn't know which way is up. Further, at small scales, the turbulent structure ceases to depend upon the nature of the large-scale flow. Macroscopically, the difference between a jet and a channel flow is marked, but on a small enough scale, as revealed by the shadow graphs, the difference in structure disappears. Because of the size difference, the similarity between the small-scale structures may be somewhat obscured. Let's change the enlargement of the channel flow. Now, they're nearly indistinguishable. This is what we mean by similarity. Similar structure despite differences in scale. Thus we find that there is a locally isotropic regime at the small scale end of the energy cascade, which is similar for all kinds of turbulence. We have already seen that the large-scale motion does not depend upon the Reynolds number. What the Reynolds number does is to determine the size ratio of the largest scales to the smallest scales of the turbulent motion. Knowledge of this behavior of turbulence provides a useful exercise in trying to outwit the movie studios. Frequently, they prefer to burn down a model rather than a full-scale set. Now, as we have seen, this deception is fairly effective because the difference in Reynolds number, which is the only major difference between model and full scale, is not apparent in the large-scale motion. The difference lies in the small scales. One of these scenes is phony. Just look at the small-scale motions and then make up your own mind which is which. In decaying turbulence, energy appears to pass from small scales to large. In fact, the energy transfer is still mostly from large scales to small. The rate of dissipation at these small scales is so great that as the turbulent field decays, it is the large-scale motions which are the last to die. Similarly, in cumulus clouds, one can differentiate between vigorously convecting clouds with their abundance of small-scale structure and those which have consumed most of their energy. It would be unwise to consider that in a turbulent flow, it is merely the Reynolds number which is of importance and that nothing else counts. In some cases, the Reynolds number may be enormous, many millions, and still no turbulence will exist because of the presence of some other influence, like rotation or density stratification, or, for conducting fluids, magnetic fields. Of these, buoyancy effects are the easiest understood. Here we have a water channel, which, partway, is divided by a horizontal partition. The flows are identical except for color. In this case, the two turbulent flows mingle fairly quickly and produce a single turbulent channel flow. Suppose we put hot water through the upper section and cold water through the lower. Buoyancy forces tend to resist the motion of fluid from the upper region. In doing the work against buoyancy forces required to raise the center of gravity, the turbulence loses energy. Stable stratification of density, that is, light fluid above heavier fluid, thus acts to inhibit turbulence. On the other hand, if we invert the situation and put the light water through the lower channel and heavier water through the upper one, we greatly increase the turbulent activity. Let's look at that again. Stable. Unstable. In the atmosphere, both stable and unstable buoyancy effects occur frequently. Here, the air close to the ground is colder and heavier than the air above it. This stable situation is called an inversion by meteorologists. Vertical turbulent motions are strongly inhibited, and any motion which occurs tends to be almost purely horizontal. Smog can accumulate when an inversion at some height above a city prevents pollution from mixing upwards. On the other hand, it is not uncommon for the air close to the ground to be heated. This produces instability and vigorous convection. Convective effects also occur in some stars, including the sun. These cells are called granulations, although most of them are more than 1,000 kilometers in diameter. They are thought to indicate convective turbulence. Convective turbulence can easily be seen in a porridge pot. In our defining syndrome of turbulence, we did not use the word random, although it would seem to have been apropos. The reason that this word was avoided was because that, at least to some people, it carries with it the connotation of a Gaussian process. Turbulent distributions are more complicated than that. One of the ways of studying turbulent distributions is with a hot wire anemometer. The output of the hot wire is proportional to the airspeed. In this record, obtained in an atmospheric boundary layer, the large-scale motion is closely Gaussian. However, if we differentiate this signal, or if we examine any other property that is strongly dependent upon the small-scale motions, we find that the property seems to be distributed in concentrated bursts, separated by regions of comparative inactivity. A stationary Gaussian process could not behave in this way. There, the derivatives would look much like the original signal, except for a change in scale. The higher the Reynolds number of turbulence, the more marked this intermittency becomes, and it is particularly noticeable in geophysical flows. This record is of temperature fluctuations in the atmosphere, and this one of velocity fluctuations of a tidal flow in the ocean. As with many other aspects of turbulent behavior, we do not have a fully satisfactory theoretical explanation for this kind of intermittency. It is another manifestation of the baffling but fascinating complexity of turbulence.